Hello, welcome to this video. This is 2A.5, and in this video we're going to talk about model selection, specifically for exponential functions, and we may revisit previous models with linear and quadratic function models. So without further ado, let's get to our learning target. We are learning to create mathematical models for a set of data or a given context, and you know you're successful if you can determine which model is best, if it's a linear situation, quadratic, or exponential. Additionally, we want to be able to construct appropriate exponential models with and without technology in order to fit a given context. And we're going to use contextual clues in order to help kind of determine which model is best and to do this. And then once we have a model, you know you're successful today if you can calculate the output of an exponential model when you have a given input. So let's get to the first idea of this lesson. How do I identify which model is best based upon a table of values or a context? Linear. Remember, linear functions grow at constant rates of change. So if you're looking over equal length input value intervals, your rate of change is going to be constant, or the change of the rate of change is going to be zero. The change of the rate of change will be zero. And then contextually, just think about something growing at a constant rate. Pretty straightforward. Quadratic, again, from a table of values, your equal length input value intervals are going to have rates of change that are linear, or the change of the rate of change, aka the second differences, those will be a non-zero constant, just some constant value. And when you're looking at exponential, your over consecutive equal length input value intervals, the outputs will be proportional. You'll get the same exact values, okay? So that's just kind of identifying, which model fits the given situation. We're going to go ahead we're going to discuss percent increase and percent decrease models, and this pertains specifically to exponential functions. When the output values of a context increase or decrease by a constant percent, the best model will be exponential of this form. F of x equals a times 1 plus r to the power of x. It's important to note a, again, will be your initial value. A is the initial value. Again, they say this here. And r is going to be your percent increase expressed as a decimal. So thinking about investments, if I have a 10% return, that 10%, your rate would be a decimal, would be 0.1. So 1.1 would be the return. The decimal is negative for a decreasing scenario. So if you have a decay situation, think about like half-life, where like radioactive material is cut in half. That R value would be a negative decimal, negative 0.5. Okay, and then positive for an increasing scenario. And then note, in order to change a percentage to a decimal, you divide by 100, right? So 10%, I divide by 100. This is 1/10, which is 0.1. All right? Okay. Now, using contextual clues in order to choose a model. I already kind of talked about this. Linear, the data values will increase or decrease at a constant rate. Quadratic, they kind of like either will increase and then decrease. They'll have a maximum, or they'll decrease and then increase. And then again, you can look at second differences if you have that. Usually contextual clues, though, you look for that increasing, decreasing. Cubic, the data values will have one minimum and one maximum. That could include volume. And then exponential, you'll have data values that increase or decrease by a constant factor. In this lesson, you may see exponential models that use what we call the natural base E. So base E is a number, and this number is approximately 2.718. And we use this often for contextual scenarios where there is a continuous change, either increase or decrease by a percentage factor. And the number is called E because it was discovered or founded by the Swiss mathematician Leonhard Euler. Okay, and it doesn't even sound like an E, it sounds like an O. And then you can see his birth year, I guess, and when he died there. So E. That's another irrational number, similar to pi, but it's approximately 2.718. Okay, we'll go ahead and do some calculator work too in this lesson, and here's just reminders about how to store a function in the TI Inspire or a value, as well as using that value, that function and value in the TI Inspire. So we'll do some of that. And then lastly, with limit notations, we don't often have vertical translations up and down for exponential functions, but if you do, you may see a limit question discussing what's the limit at either positive or negative infinity. At negative infinity, an exponential function will approach, remember, the horizontal asymptote. So this is your horizontal asymptote value. And if you have a shift of d, right, so if you move this function up d amount, the limit at negative infinity of f of x is going to equal that d value. And then if you have a c value that's negative, if you get that horizontal reflection, so now your function looks like this, or something like exponential decay, again, you're going to have a horizontal asymptote here at y equals d. So just note that you may see questions like that, okay? So without further ado, let's go ahead and look at some examples and kind of rope in all of that idea. First idea here that we're going to see is the table of values of a function g of x. Determine whether the values in the table are best modeled by linear, quadratic, or exponential function. Okay, so I'm going to go ahead and I'm going to look at my function and I'm going to try to determine if this is linear, quadratic, or exponential. So just looking at this, 3 to 9, I have a difference of 6 here. 9 to 27, going to increase by 18. And then 27 to 81 plus 4 takes me to 31. So is that 54? Okay, so definitely not linear, right? Because they're not constant. And if I look at my second differences here, I have 12, and then plus 6 would take me to 24. So is that 26? We get 24 plus, no, is that 36? Plus 36. Okay, so, yeah, I mean, that's not constant, right? They're not increasing by a linear rate, so it's not quadratic. And maybe you can just see this ratio, right? Where if I take my terms, and actually you can see this multiplying factor, right? So from 3 to 9, we multiply by 3, 9 to 27, multiply by 3, 27 to 81, multiply by 3, and then you can also see this in my rates of change as well. So all of these ratios, right, 18 divided by 6, we have 36 divided by 12, all of these have a common ratio of 3. Common ratio of 3. So this is exponential. Exponential. All right, part B, they say give a reason based upon the change in the output values of the function and the input values of the function. Well, we can say over consecutive equal length input value intervals. The outputs are proportional, or the rates of change are proportional. Okay, so there's that E-Livy statement, and the outputs are proportional. All right, here is another example. Please go ahead, pause me, and then try this practice problem. Okay, hopefully you got quadratic function. You can look here and see the first differences, 9, 15, 21, 27. It's not constant, so it's not linear function, but the second differences are constant. The change in the rate of change is constant, and that's our justification for quadratic function. Over consecutive equal length input value intervals, the change in the rate of change is constant. You could also say the rate of change is linear. That would also be effective. Okay, so that's finding functions model selection from a table of values, which we have done before. Next, we're going to go ahead and get into some exponential context situation, and these are pretty prevalent. We're going to be given a context and then have to identify the function type. So, example 1, the value V in dollars of a truck purchased new for $28,000 in 2015, t equals 0, depreciates or decreases in value by 9.5% each year for the first 10 years, from 0 to 10. Which of the following function models the value of the truck in dollars t years after 2015? So a couple things. It's important to note they give us an initial value. This truck was initially bought for $28,000 in 2015. And they tell you it's depreciating. It's depreciating. So this is the R value. It's depreciating. The percentage is negative 9.5% each year. So expressed as a decimal, this is going to be negative 0.095. And again, you can get this by just dividing by 100. We get negative 0.095. So for an exponential model, remember we're multiplying by this loss of this value each year. We're losing 9.5%. So really, you still retain 90.5% of the truck's value. Okay, and that's what you multiply by each year. I know I'm losing almost 10%, but I'm keeping 90%. You can think about it that way. I guess if you're an optimist. So here's the value of the truck. V of t equals, I'm starting out with $28,000, right? This is your A value. And now I'm going to multiply times 1 plus R, or in this case, our R value is negative. So 1 minus 0.095, and this is raised to the power of t. So this happens every single year. So notice you don't see the 1 minus 0.095, but you should think, hey, this value is going to have to decrease. So it's definitely not A, that's just the 0.095, that's just our R value. D, they're thinking that you don't understand that the percentage has to be converted to a decimal. So we're between C and B. C, you have that 9.5% added to 1. This would be an exponential growth if your truck was gaining value. B is the answer if we decrease 1 by 9.5%. By take away 0.095, we get B. Okay, so answer is B. All right, here is a practice problem. The population in Mali was 7.09 million in 1980, t equals 0. Since that time, the population P has increased on average 2.07% per year. Which of the following functions models the population in Mali in millions t years after 1980? Pause video, please try this example. All right, hopefully you had a chance to go ahead and find the function that models the population in Mali in millions. So it's important to note we're starting at A equals 7.09. I can't eliminate any options based upon that. It's important to note too that the function is increasing. Your population is growing. So this is going to be exponential growth. So anything where I'm not above 1 is going to bite the dust. So like C, I can throw that out because that's not going to cause exponential growth. My function here, P of t, what they call it, we start out at 7.09 and we're going to multiply times 1 plus our R value, which is 0.207 to the power of t. So it looks like our answer is A. Oh wait, why did I cross it off? That's our answer, A. B would be if you were growing 20.7%, 20%. Okay, you didn't move the decimal far enough if you selected B. And then D, that's not it. Okay, that's if you didn't convert to your R value and add 1. Okay, if you don't know if you figure out the trick here, when you're dividing by 100 to go from percentage to your R value, you just move the decimal 2 places. 2 places. Okay, all right. So if you could generate a function, you're successful in being able to select the appropriate model there. Okay, couple of examples. These are kind of straightforward, and we're going to talk about a given context and what's the appropriate model. Each month, Mark increases the amount he gives to charity by the same amount. Which statement with reason fits the best model? This is linear because there's a constant rate of change. Yes, that's it. Giving the same amount, increasing the same amount, that's it. I don't even need to read the rest. Quadratic, no, nothing's changing there. Exponential, no, it's a constant factor. And then B, cubic, because the function's always increasing. No. Well, I mean it is, but that's not it. Okay. Each month, Mark gradually decreases the amount he gives to a charity, and then he slowly returns the amount which he originally gave. That sounds like a quadratic because he's decreasing, and then he starts to go back to the amount that he originally gave. So it's not linear because there's not a constant increase or decrease. Quadratic model because there is a clear maximum. No, I mean we're decreasing and then increasing. I would say C. There is a clear minimum. All right, next example. Each month, Mark doubles the amount he gives to charity. Dang. Which statement with reason best fits the context? Not linear, because that's not a constant rate of change. We're doubling. Exponential model, because there is a constant rate of change. Well, constant rate of change, again, is linear. Exponential model, because it's because the amount always increases by a factor of 2. Yep. It's not quadratic. It does increase by a factor of 2, but that's going to be exponential. All right. So let's go ahead and look at the next example. Here they say a person invests $5,000 in an account that earns 3.5% annual interest compounded continuously. The function v of t equals 5,000 e to the power of 0.035 t models the value of the account t years after it's opened. A. Find the average rate of change of the account in dollars per year from t equals 10 years to t equals 15 years. Explain what this average rate of change means in terms of the context of the problem. Okay, so I'm going to revisit here average rate of change. And remember, average rate of change is always your function value at your second input minus your function value minus your first input over your second interval point minus your first interval point. So in this case, and I know I used x, it's t's here, we're going to go ahead and we're going to plug in these function values. So what is the value of the account after 15 years minus the value of the account after 10 years over 15 minus 10. It's important to note this is called the difference quotient. You always want to include a difference quotient in your average rate of change. And then we're going to go ahead and find these values, or we can just use a calculator in order to spit this out. So this is calculator active. We're going to go ahead. You want to have your calculators, and I'm going to store this function and then use it to help me compute the average rate of change. All right, so here's a calculator. I'm going to go ahead. This is for a TI Inspire. So if you have a TI Inspire, I'm going to open up a calculator. This is on your front page, reminding you how to store a function. So we can store a function 5,000 times e. E is right here next to 10 to the power of x, e to the power of x. So e to the power of, and we have 0.035 times t. And I'm going to use x. I just like to keep the inputs simple. And then move over, and I'm going to store it. Again, store is the secondary function to the VAR button. So store it, and I'm going to call it, let's call it v. V of x. And you hit enter and it'll say done. I now have v. So if I want to go ahead and calculate average rate of change, I can enter a quotient, and I want v of 15 minus v of 10 over 15 minus 10, which we know is 5. And then there is our value. So this is 271.391. 391. Okay. So I have entered that value here. Now, the second part of this says explain what the average rate of change means in terms of context of the problem. So what does this even mean? I like to use the acronym CUT for remembering what to include. I like to include, first of all, the context. What are we talking about? Well, they say here the function models the value of the account. So we can say the value of the account, and you always want to say if it's increasing or decreasing. So this is a positive number, is increasing on average 271.391, and we now want to include units. That's what the U stands for. So it's important to note the value of the account. This is in dollars per year. This is in dollars, and time is in year. And they actually tell us this here, in dollars per year. They're very kind. So dollars per year. Dollars per year. That's units. Context. Units. And then T stands for time. You want to be specific because average rate of change is only over a certain interval. So this occurs from T equals 10 years to T equals 15 years. Okay, acronym CUT. That's how you remember. Context, include the context. The value of the account is, what's it doing? Is it increasing or decreasing? You put the value. If it's negative, you would say decreasing, and you don't need to include the negative. And then you include the value. Okay, part B. Determine after how many years the value of the account will reach $7,000. Ooh, write your answer as a decimal approximation. So they want to know when will this value of the account, when will V of t be equal to $7,000. This is a calculator problem. You're going to go ahead and solve by graphing. You're guaranteed to have one of these questions on your AP exam, either on FRQ1 or FRQ2. So I have my function. I'm going to go ahead and graph it. Some of my students are like, that's why you always tell us to graph it first, because now you have a picture of it. Yep. So I can graph my function v of x, and then I'm also going to graph 7,000. And I'm going to be way too low. I'm going to have to zoom out. So menu, I'll change my window, settings. Let's make this 7,500. And I'm able to see the intersection there. Okay, so menu, analyze graph, intersection. Left, right, and we get 9.613. So t equals 9.613. All right, and that's all you need. It says write your answer as a decimal approximation. There you go. Okay, couple of practice problems to close out this lesson here. Please read this context, and then I'll go over question A and B, and then talk about this last practice problem down here. All right, hopefully you defined your function B in your calculator, 17e to the power of 0.31x. I'll graph that, so my function's defined. Go back to the calculator, and now that you've defined your function, for me here it's f of 3, you can calculate the function at 8. So our answer here is that b of 8 is equal to 203.001. And then they say, explain what this means in the context of the problem. Well, we're talking about a population of bacteria growing at a rate of 3.1%. So that's the number of bacteria after 8 hours. So we could say after 8 hours, there is 203.001 bacteria. Was it 001? It was 001. Okay, so that's what it meant in context. After how many hours will the number of bacteria reach 1,000? Write your answer as a decimal approximation. So again, you're going to go back to your graph, and you're going to graph 1,000, and then you're going to solve this by finding the intersection. So hopefully you went ahead and graphed 1,000. We can see the intersection over here. So menu, analyze graph, intersection, and your value should have been 13.147. So t equals 13.144. 144. Okay, hopefully you did pretty good. We've kind of done stuff like that. We're just kind of incorporating some exponential context. All right, the last practice problem I have for you, I've talked about this at the opening part of the lesson. If you have an exponential function, d of x equals a times e to the power of negative 2.3x plus b, where a and b are integers, they give us values here. They say if d of 0 equals 12 and the limit is equal to 2, which of the following is an expression for d? I'm going to go ahead and kind of talk you through this one because we haven't done anything just like this. It's important to note, they say if d of 0 is equal to 12, this is an initial value, So that would help you solve for your a value. A is equal to 12. And I know it's an initial value because a is your input value, x is 0. You could go ahead and plug in your value here. You could plug in 0, and you would get a, so d of 0 equals a times e to the power, if it lets me write, of 0, which is 1. So 12 is equal to a plus b. Ooh, I lied to you, actually. It's not 12. You gotta get your b value first. The limit as x approaches positive infinity equals 2. So here they're telling you if you go to positive infinity, you're going to get a value of 2. So this being exponential decay, your function here is decaying at a rate, and you're going to get 2. So that means b is equal to 2. And if b is equal to 2, then your a value is equal to 10. If we subtract 2 here. So a is equal to 10. A is equal to 10. So our answer, it's not going to be a and b. Those are good distractors. But it's going to be C. C is the answer. I was like, what's the difference between C and D? Okay. All right. So that's going to do it for this lesson. We went ahead and selected appropriate function models for exponential models based upon given situations. All right, give the video a thumbs up. See you in the next video.